Hello, everybody. Welcome to our wearable technology senior design. This is our obstacle detection device for the visually impaired presentation. For this design, our advisor was Dr. Carlos Castro Candelas. I am Husam Elyo.
I am Sotez.
I'm Kristina Pekson.
And I am Xavier Lomeli.
For this presentation, we're going to be going over our objective, design process, design overview, results, issues and solutions, project costs, schedule, future improvements, and then conclusion, and finally references and our Arduino code. The purpose of our project is to create a hands-free device used to aid the visually impaired scan their surroundings for elevated obstacles which cannot be detected by a white cane. This device can also be used in addition to a white cane to help onlookers identify the user as visually impaired and take appropriate care. This device is also hands-free, easily worn, and easily stored. As for the design process, we started by defining the problem and goals, and then researched components for distance sensor and outputs, tested code on components individually, and then verified specs for individual components, tested distance sensor under different temperatures, and then finally assembled the project and then tested the overall code.
Before discussing the final design, we would like to first briefly show alternative designs we initially considered pursuing, but eventually scrapped, namely the visor frame, seen on the left of the screen, the earpiece frame shown on the right, and a glasses frame not shown. Ultimately, we opted for a design as compact and impact resistant as possible. Hence, our decision to proceed with a patch capsule casing, seen here, made of PLA plastic. This particular patch model is designed to be chest mounted and attaches to the user's shirt or blouse with either a strap slot variant, center image, or clip variant, right image. Protruding from the side of the casing is the vibration motor, which when activated will be felt on the user's chest. On the underside of the casing are various ports for battery and Arduino access. The front plate features a cylindrical envelope for the ultrasonic sensor, as well as the power switch situated just above. Here is an exploded view of the assembly. Clearly, the battery dictated the size of the overall casing. And now an alternate view. The only parts that we 3D printed were the casing, front plate, and strap slot. And here are their respective drawing files. First for the casing, then for the front plate, and for the strap slot. Lastly, here is an FEA analysis with an applied force of 10 newtons of both the clip and strap slot, which will be subjected to the greatest stresses. This force is greater than the parts would normally be subjected to, which explains the deformations.
Now I will be going over through the main design components. These 5 components were chosen after research and testing to ensure that the best components for obstacle detection was being taken. For distance measuring, the LV Maxonar EZ0 ultrasonic sensor was used. This served as the input that was sent to 2 outputs, an audio and a vibration output. Reasons on why these 3 were chosen will be explained in the next couple of slides. The device is also powered by a 5-volt power bank. Lastly, the housing was 3D printed. As I mentioned before, the EZ0 sensor is the input that measures distance. It works by transmitting a high-frequency sound and measures the time to be reflected back. Then it converts it to distance. A major point that made us choose the sensor was that the range offered goes beyond what we need to be detected. Specifically, it goes up to 254 inches, which is approximately 21 feet. The operating temperature includes a wide range that was later tested. The sensor is also known to be used for people and long-range detection. Out of the entire EZ series, the EZ0 offers the highest sensitivity for the user and is able to detect objects at a wider range. Although the EZ0 sensor was decided to be the official sensor for the project, an IR sensor was also considered but not part of the final design. It was used to compare the data with the EZ0. Some of the main disadvantages that ruled this sensor out as an option for the project include one, that the lens is always supposed to be clean, and it is mentioned in the datasheet that dust, water, oil, and more can actually deteriorate the characteristics of the device. And the second point is that sunlight or specific lamps can reflect light on the object it is detecting and cause faulty readings.
As for the audio output device, we decided to go with the audio MP3 jack as it is compatible with most standard earphones, made specifically for Arduino, and can withstand high voltage ranges and insertion forces. It has a long operating life and can be operated under a wide range of temperatures. As for the physical output, we decided to go with a vibration motor as it has fast speeds and can be easily detected by the user, designed to be compact as much as possible, suiting our compact design, and it is also used in a wide variety of products.
So now we will be going over testing that was conducted. The IR sensor was used throughout the project for comparison and during testing. According to the datasheet, the IR sensor's voltage versus distance does not behave linearly. Therefore, a calibration was completed to simply plot plot the reading versus distance. This gave very accurate readings when testing the sensor. As seen in the figure, 5 trials were taken per distance and created a line with an R-squared value of 0.9426, which is pretty accurate. The equation of the line was then used to convert the reading to output the distance. The next test was a verification of function under different humidities for the analog and digital values of the EZ0. A note that I want to point out is that the Maxsonar datasheet states that each time the sensor is powered up, it recalibrates its first read cycle. However, if the temperature, humidity, or applied voltage changes during operation, then the sensor may require recalibration, which may slow down the output for an accurate reading. During this specific test, the humidity was constantly changing from high to low. This is most likely the main source of error as to why all data points do not fit exactly at 20 inches, especially the EZ0 analog test, which stays pretty much constant at 25 inches instead of 20. The last test conducted so far is a temperature test for the analog and digital values of the EZ0. For this procedure, the sensor was set to a specific temperature, then multiple readings were recorded from that temperature. This way, the note about the sensor recalibrating if the temperature changes is considered and avoided from error. As seen in both plots, there was slight error as the test approached 100 degrees. The team is currently still conducting tests and plan to do more tests to verify the voltage versus distance of the EZ0 sensor in the final product assembly. Here, the components were set up to demonstrate the functionality of the device, while the 3D printed housing is currently still being assembled. To explain how the device works, the code sends a fast output if the distance is 0 to 3 feet away, and a slow output if it is 3 to 5 feet away. This video demonstrates an obstacle detection test where an object was placed 80 inches away, resulting in no output, then 45 inches away, resulting in a slow output, then lastly 20 inches away, which results in a fast output. In case the video sound does not appear in the recording, the link is provided below for any viewers to check out. This demonstrates the slow output, and that demonstrates the fast output from the vibration motor. For the audio output, This demonstrates slow output and fast output.
Currently working on reviewing our final results. But once ready, we plan to test the accuracy of the EZ0 sensor by recording how it behaves when placing an object in front of it at different distances. We also want to test if the device can detect objects while walking and corners and hanging objects. We found that adding multiple components and having loose wires affected the EZ0 sensor readings, so we eliminated breadboard connections and soldered wires together. We also had faulty readings when we had the IR and EZ0 sensor working together, so we tested them separately and found that the EZ0 sensor worked best. These are our final design costs. The total came out to $82. These are our additional project costs, which includes all the items we tested with and the materials we were considering on using in the final design, but were not used. The total came out to $81. This is our schedule for the entirety of the project. We found that the most time-consuming portion was the prior research and brainstorming and finalizing our model, but were completely necessary in creating our final product. In the future, we want to be able to tell the user the exact distance of objects and make the design more compact by finding a smaller battery. We found that the EZ0 sensor gave out faulty readings many different times, so you want to be able to reduce or even eliminate any noise. On some occasions, our nano would heat up, causing our pins to burn out. To determine the cause, we would need to do more testing. Additionally, we want the device to work under multiple conditions, such as in the rain or in a crowded area. Lastly, we want to be able to offer the user a wireless, water-resistant, and cheaper device.
So overall, we determined that we could make our device more accessible to the user by giving out the exact distance of objects and altering it to perform under multiple conditions. Also, the device's overall usefulness can be improved further based on the feedback of the visually impaired community. With proper testing of materials, it can help achieve improvements since some materials did not behave as expected. These are our references, and this is our compiled Arduino code.